So today is the day that takes everything we've been doing with indefinite integrals or definite integrals and kind of creates that connection. So what we're going to talk about is two parts. And the fundamental theorem of calc essentially says that the derivative of the integral just becomes the function inside, which should make sense. The derivative and the integral are like canceling functions. So that's pretty much what part 2 of the fundamental theorem of calc says. So going into like those details, if f is our function and it's lowercase f, we have the interval a to b. On that interval, we have a continuous function. Then the part 1 to the fundamental theorem says that the function capital F of x is equal to the integral from a to x of f of t. We'll have a derivative at every point x in AB, and that the derivative of f, capital, or the derivative of the integral a to x f of t, will therefore equal f of x. Part 2 is what we've been talking about. However, now it's going to be manipulated in a way that if we have an initial condition as well as a given area, we can find a different point. So it says that if capital F of f is the antiderivative, then the integral from a to b of f of x dx equals capital F of b minus capital F of x. So the first fundamental theorem of calculus is sometimes referred to as the net change theorem. The fundamental theorem of calculus is sometimes referred to as the net change or total change theorem. The definite integral of a rate of change is thus equal to the net change in the original function. And that's what I think is important. This inside the integral is the derivative. This is the equal to the original points. So it might be given to you that f of 0 is 3. That would be considered an initial condition. So that would be an initial condition. We're going to use the integral to find the area under the curve to find the displacement or the ending position. So this allows us to find the end position at an exact spot. We will often see this theorem or fundamental theorem part written as f of b equals f of a plus the integral from a to b of f prime x dx. So you will often see it rewritten in the following way. This is where f of b is considered our end amount, or where it is at the end of the interval. F of a is what we will refer to as an initial amount. And again, the integral represents the change. So f of a is initial, integral is change, f of b is final. So typically, if you're using part 2 of the fundamental theorem, one of the easiest things to do is to graph the function. That allows you to check for continuity. You're also looking for breaking points on that interval. So if you don't know what a function looks like, then you can graph it. Then we're going to use our previous methods from the prior section, which is our reverse power rule, our natural log rule, our e to the x, and our sine rules. And then we're going to plug in the values to the antiderivative, subtract the values away, and add in that initial condition. So, for example, if I ask you to simply evaluate that integral, then this is like the old. So we're going to evaluate the integral from -2 to 1 of x cubed dx. That becomes 1/4 x to the 4th, evaluated from 1 to -2. Plug in our 1. Plug in our -2. So I get 1/4 minus 2 times 2 times 2 times 2 is 16. So you get -15 fourths. That represents the net change. This represents net change. So what that means is on the integral of x cubed, which looks roughly like this, at -2 to 1, the area below is greater than the area above, therefore the net change remains negative. Same idea, different function. So what is the net change of the integral from -3 to 1 of 1 over x squared? So again, taking into account 1 over x squared, this is going to have a vertical asymptote at 0. So is that curve continuous on that interval? Can I find a net change? No. So you can only integrate functions that are continuous. So if a function is not continuous, then it cannot be evaluated. So there is no net change because x to the -2, or 1 over x squared, is not integratable over the interval -3 to 1. Okay? So then I accidentally photocopied the same page twice, so you're just gonna like put a little X on that one. Oh wow. Oh, that happened when I put it in the copier. I must have like add that. So now we're gonna evaluate the integral from 1 to 3 of 5x to the 4th. So why is this integratable but the last one was not? Because of the interval. So even though 1 over x to the 4th or 5 over x to the 4th is not integratable at 0, it can be integratable over a different interval. So now we're looking at from 1 to 3. So this is really the same as 5 out in front 1 to 3 x to the negative 4 dx. So the 5 is our constant. Its property says it tags along. Our rule says we add 1 and divide by that new power. So negative 4 plus 1 becomes negative 3. Divide by negative 3 and evaluate from 3 to 1. So I get 5 over negative 3x cubed, evaluated from 3 to 1. So the net change is 5 over negative 81 minus a minus, so a positive 5 over 3. And then technically on AP, that is considered a numerical answer. If you have a calculator and you add them together, you get 130 over 81. And again, that should make sense because here we'd be multiplying by 27 over 27 to get this to 81. So 5 times 27, well 5 times 25 is 125. So 5 times 2 more is 135. So you have 135 over 81. So you'd only take 5 away from that, and you get 130 over 81. So that means the net change or the overall sum is positive. So you're sitting there going, okay, what's new? So the new part is what we're going to do with a graph and down below now. So in that graph down below, I kind of feel like that's not good. We have finding net area. If f is a function whose graph consists of 2 straight line segments and 2 quarter circles as shown in the figure below, and g of x equals the integral from 0 to x of f of t, find the following. So if you wanted to find g of 0, then what you're going to do is essentially say, okay, g of 0 equals the integral from 0 to 0 of f of t dt. Well, what do we know about the integral from 0 to 0? So g of 0 equals 0. That is now considered my initial condition. All of the remaining information is going to come by combining that g of 0 with my graph. So now, if I want to find g of 1, it's going to be equal to g of 0, which is nicely 0, plus the integral from 0 to 1 of f of t dt. So g of 0 is 0 plus 0 to 1. So area under the curve is 1/2 base times height. Height is 2, base is 1. 1/2 times 2 is 1. So 1 and 1 makes 1. So g of 1 is 1. G of 2 would equal g of 0 plus the integral from 0 to 2. So you have 2 ways you could go about doing that. You can take what we know, which is 0 to 1, add 1 to 2. So we get 0 plus 1 plus 1 to 2, which is 2. So g of 2 is 3. G of 4 So now it says that it is 2 straight line segments and 2 quarter circles. So now from 2 to 4 is a quarter circle. So its area is 1/4 pi r squared. Where again, my radius is from 2 to 4, so my radius is 2. So 2 squared is 4. So 1/4 of 4 is pi. So this area right here is pi. This area is negative pi. So the integral from 0 to 4 is 3 is pi. So g of 6, when you think about a quarter circle, well now that graph is going to be above and below. So we have this area that is going to essentially cancel within itself. So g of 6 is equal to g of 0 plus 0 to 4 of f of t dt. So you get that 0 to 6. But we know that the integral from 2 to 4 and 4 to 6 wipe each other. So this is really the same as the integral from 0 to 2, which means it's going to be plus 2 plus pi minus pi, or simply 2. Sorry. So how would taking the derivative of that change it? So if you take the derivative of the integral, that's part 1 of our theorem. So g prime of 1, or g prime of x in general, would be like taking the derivative of the integral from 0 to x of f of t dt. So g prime would be like taking the derivative of the integral, which means g prime is simply f of x. So g prime is simply f of x. So that means g prime of 1 is like f of 1, which is g prime of 4 would thus be equal to f of 4, which is 0. G prime of 6 would be f of 6, which is negative 2. So then using all of that information, we're going to, on the top of the next page, sketch a possible graph of g in that coordinate plane. So again, g is going to come from all of these. So you're going to sketch or plot 0, 0, 1, 1, 2, 3. Four, and then 3 plus 5, pi is like 3.14. So 3 plus 3.14 is kind of like 6.14. 6 is back at 3. And then the derivative part simply helps you understand the slope. So if the derivative is positive, then my original graph is increasing. If my derivative is 0, my original graph is at a maximum or min. And if it's negative, then it's, yeah. So all of that kind of makes sense to like this graph in a way though, right? So here, segment, segment, curve. Ooh, that was terrible. You can see that externally. You can see that. It doesn't even kind of make sense. This is like a quadratic. If G prime is F, G prime is F, this is coming before. So this is like capital F of X. So if that's kind of a constant or a slope, you can see how they play in together. We're going to stop there. We'll do example 2 and beyond tomorrow. No, Thursday.